Welcome to Sleepy Cosmic Lore. Tonight, we're following the moon's incredible journey, from a violent birth that reshaped Earth to the quiet companion that changed our oceans, our time, and perhaps even the story of life itself. If you enjoy relaxing space documentaries like this, please take a moment to like the video and subscribe. It may seem small, but it truly helps this channel grow. Thank you. And now, let's begin. Long before the moon became a pale circle above sleeping oceans, before there were oceans at all, the young solar system was a place of astonishing violence. Roughly 4.5 billion years ago, the sun had only recently ignited, and around it swirled a vast disk of gas, dust, metal, and shattered rock. Within that disk, grains collided and clung together. Small bodies grew into larger ones, and larger ones began pulling everything nearby into increasingly dangerous encounters. Planets were not born peacefully in empty lanes. They were assembled through impact after impact. Each collision, adding material, changing direction, releasing heat, and sometimes destroying nearly as much as it created. The early Earth emerged inside this chaos as a glowing, unstable world, its surface repeatedly melted by incoming objects, its interior separating into layers as heavy iron sank toward the center and lighter rock rose above it. There was no blue sky, no quiet coastline, and no moon. Then something happened that would permanently divide the history of Earth into two worlds. According to the leading scientific explanation, a large planetary body struck the young Earth with enough force to reshape both objects. Scientists often call this hypothetical body Theia, after the mother of the moon goddess in Greek mythology, though the name should not make it seem more certain or familiar than it really is. No telescope ever saw Theia. No intact fragment has been placed in a museum. It is a reconstructed world, inferred from physics, chemistry, computer simulations, and the strange relationship between Earth and the moon. The traditional version of the giant impact hypothesis imagines Theia as roughly comparable in size to Mars, approaching Earth at an angle rather than hitting it head-on. A direct collision at extreme speed might have shattered the planet or thrown too much material away, while a grazing impact could strip rock from the outer regions of both bodies and send it into orbit. In a matter of hours, the sky above the wounded Earth may have filled with incandescent debris. Vast streams of molten and vaporized rock would have circled the planet in a glowing disk, brighter and hotter than anything that has existed above Earth in human history. From this orbiting material, gravity began gathering fragments together. Collisions that would once have destroyed small bodies now helped build a new one. What emerged was the moon, although the exact path from impact to finished satellite remains one of the most active and fascinating parts of the story. Some models suggest the orbiting debris gradually collected over months or years. Other simulations indicate that a large, moon-like body may have assembled with extraordinary speed, perhaps within hours after the collision, while smaller material continued to fall onto it afterward. These scenarios do not necessarily reject the same central event. They show how difficult it is to reconstruct a process that occurred before the oldest surviving rocks on Earth had even formed. The event was not recorded by cameras or written into an untouched layer of crust. It must be rebuilt from what the collision left behind. One of the strongest clues is the moon's unusually small metallic core. Earth has a large iron-rich core because, during its early molten state, dense metals sank inward. If the moon had formed as an entirely separate planet beside Earth, scientists might expect it to contain a larger proportion of metal. Instead, the moon is dominated by rocky material, much like the outer mantle of a differentiated planet. A giant impact offers a logical explanation. Much of Thea's dense metal may have merged with Earth, while the material thrown into orbit came largely from the rocky outer layers of the colliding worlds. Yet this apparently neat answer soon creates a deeper problem. If the Moon formed mostly from Thea, then lunar rocks should carry a chemical identity noticeably different from Earth's. Every planet and asteroid formed from a slightly different region of the early solar system, and those regions often possess distinctive isotopic fingerprints. Isotopes are versions of the same chemical element with different numbers of neutrons, and their ratios can act like a record of where material came from and what it experienced. When Apollo astronauts returned lunar samples, scientists found that Moon rocks and Earth rocks were astonishingly similar in several important isotopic systems, including oxygen. The resemblance is so close that it has become one of the greatest challenges to the simplest impact model. Was Thea formed near Earth from almost identical material? Did the collision mix the two planets so completely that their original chemical differences were erased? Or did most of the Moon actually come from Earth rather than from Thea? Each possibility changes the violence, speed, angle, and aftermath of the impact. This is where the story becomes more interesting than the simplified image of one planet striking another like two billiard balls. A collision on this scale would not behave like solid objects bouncing across a table. At planetary energies, enormous regions of rock would melt, vaporize, compress, and flow almost like fluids. Earth may have become surrounded by a thick atmosphere of silicate vapor, with temperatures high enough to turn ordinary stone into gas. Material from Earth and Thea could have circulated through this shared cloud, exchanging heat and matter before the Moon fully assembled. Some researchers have explored the possibility that the impact produced a structure known as a synestia, a vast, rotating mass of vaporized rock shaped less like a planet with a ring and more like a swollen, spinning cloud, with no sharp boundary between Earth and the surrounding disk. Within such an environment, the Moon might have formed while chemically connected to Earth, helping explain their remarkable similarity. It is an elegant idea, but elegance is not proof, and scientists continue testing whether such models match the Moon's composition, Earth's rotation, and the total angular momentum of the system. Angular momentum is another piece of the puzzle because the Earth and Moon do not merely exist side by side. They form a linked mechanical system. Earth rotates, the Moon orbits, and the combined motion carries a measurable quantity that any origin theory must reproduce. Some proposed impacts create too much angular momentum. Others produce too little lunar material or leave the Moon with the wrong chemistry. A successful explanation must satisfy all these constraints at once, which is why researchers have considered multiple variations. A relatively slow collision with a Mars-sized body, a faster impact involving a smaller object, an energetic collision between two bodies of more similar size, a hit-and-run encounter followed by another impact, or even a sequence of smaller collisions whose orbiting debris gradually built the Moon. The multiple impact idea is especially provocative because it replaces one decisive catastrophe with a series of lesser ones, each producing a temporary small moonlet. Over time, these moonlets could merge. Such a process might help explain some chemical features, but it also introduces new questions about whether the moonlets would survive, collide correctly, and produce the present system. The giant impact family of models remains the strongest general framework, yet the precise identity of the impactor and the exact sequence of events are still not settled. The Moon's lack of many easily vaporized substances also carries the signature of extreme heat. Compared with Earth, lunar material is depleted in several volatile elements, substances that tend to escape when temperatures become high. This fits a hot, energetic origin. But even here, the evidence refuses to form a perfectly simple picture. Lunar samples contain traces of water and other volatile materials, showing that the moon was never quite as completely dry as earlier generations believed. Some of that water may have survived the impact, some may have been delivered later, and some may have come from the solar wind interacting with the surface. The challenge is not merely explaining why the moon lost so much volatile material, but how some of it remained. Even the age of the moon must be approached carefully. Most evidence indicates that it formed very early, probably within the first 100 million years of solar system history. But estimates differ depending on which isotopic clock is examined and what event that clock is actually dating. A mineral may record the initial impact, the cooling of a magma ocean, or a later episode in which the rock was reheated. The moon's oldest surviving minerals are messengers, but they do not always speak about the same moment. This uncertainty is not a weakness in the story. It is the reason the moon remains scientifically alive. Every sample contains several histories layered together, and separating them requires the same patience used to reconstruct a burned book from fragments of individual pages. What seems clear is that the collision did more than create a satellite. It transformed Earth. The impact likely remelted much of the young planet, altered its internal structure, and may have changed the orientation and speed of its rotation. The metallic core of Theia, if it existed as imagined, may have joined Earth's own core, while its rocky mantle became mixed with terrestrial material. In that sense, Theia may not have vanished. Portions of it could still be buried deep inside Earth, incorporated into the mantle and core, while other portions may survive in the moon. Some researchers have suggested that unusual structures far below Earth's surface could contain remnants of the impactor, although this interpretation remains debated and is far from proven. The thought is haunting. The lost world that helped create the moon may still exist, not as a planet, but as chemically altered material hidden beneath our feet. After the impact, the newborn moon would have appeared enormous in Earth's sky because it orbited much closer than it does today. Both worlds were incandescent, scarred, and still changing. The moon was not yet the gray, silent desert seen through modern telescopes. Its surface may have been almost entirely molten, shining with its own heat rather than merely reflecting sunlight. Earth below was also hostile, wrapped in vapor and recovering from one of the most energetic events in its history. Yet out of this devastation came an enduring partnership. The moon would slowly move outward. Earth's rotation would gradually change. Their gravitational interaction would shape the length of days, the movement of oceans, and the stability of the planet across immense spans of time. None of those consequences were planned or inevitable. They followed from one collision among countless collisions in a violent young planetary system. Had Theia been smaller, faster, slower, or traveling along a slightly different path, there might have been no moon. Several moons, a moon with a different composition, or perhaps no surviving Earth resembling the one we know. This is why the origin of the moon is more than a question about an object in the night sky. It is a question about contingency, about how a narrow sequence of physical events can redirect the future of an entire world. The catastrophe did not simply leave Earth with a companion. It produced a second archive of the solar system's beginning, a world whose rocks would one day allow distant descendants of that collision to reconstruct an event no living creature could have witnessed. But before the moon could preserve that history, it had to survive its own inferno. Beneath its glowing surface, heavy materials were beginning to sink. Lighter minerals were beginning to rise, and an ocean made not of water but of molten stone was slowly preparing the first crust of a new world. The newborn moon did not begin beneath a black sky as a quiet gray sphere. It began as light, an entire world glowing from the heat trapped inside it, its surface blurred by molten rock. There were no craters yet, no powdery plains, no familiar dark seas, and perhaps no solid ground anywhere a traveler could have stood. The energy released during the moon's assembly had been converted into heat so efficiently that much, and possibly nearly all, of its outer body became a vast magma ocean. This was not a shallow field of lava like the flows that later crossed parts of the lunar surface. It may have extended hundreds of kilometers downward, turning the early moon into a planetary furnace whose interior had not yet decided what kind of world it would become. The first great act in that transformation was separation. Molten material does not remain chemically uniform forever. As temperatures fell, different minerals began crystallizing at different stages, each carrying certain elements out of the liquid while leaving others behind. Dense early minerals rich in magnesium and iron, including olivine and pyroxene, tended to sink through the remaining melt, accumulating below like dark mineral snow falling into a glowing abyss. This process gradually built much of the lunar mantle, layer by layer, shaped by pressure, temperature, convection, and the constant rearrangement of material. The moon was becoming differentiated, a small metallic core at the center, a deep rocky mantle above it, and eventually a crust at the surface. Yet the most visually important mineral in this story did something that seems almost backward. Plagioclase feldspar, especially a calcium-rich variety, was less dense than the liquid around it. Instead of sinking, its crystals floated upward. Over time, countless pale crystals gathered and fused, creating a primitive crust dominated by a bright rock called anorthosite. The ancient lunar highlands, the light-colored regions still visible from Earth, are largely the battered descendants of that first flotation crust, and their widespread anorthosite is one of the strongest reasons scientists think a global or nearly global magma ocean once covered the moon. NASA's current overview notes that anorthosite forms by crystallizing from magma and floating upward, and that its broad distribution points to an early molten layer, potentially hundreds to thousands of kilometers deep. The image is strange, an ocean of liquid rock slowly freezing while its lightest crystals rise like ice on water. Except the ice is glowing feldspar, and the ocean beneath it is hot enough to melt mountains. But the first crust was not a smooth, permanent lid. It was thin, hot, and fragile. Convecting magma below could disturb it. Newly rising crystals could thicken it unevenly. Large fragments might founder back into the melt, while other regions were rebuilt. The crust likely grew through repeated flotation, remelting, intrusion, and disruption, rather than in one clean freezing event. This matters because the traditional picture of a perfectly layered moon, a core, mantle, magma ocean, then a uniform floating crust, is useful, but nature rarely follows diagrams so obediently. Lunar rocks reveal mixing. Some early crustal samples contain chemical combinations suggesting that material from different depths interacted, and later magmas intruded the primitive shell before it had fully stabilized. Even the depth of the magma ocean remains debated. Earlier estimates often assumed a very thick crust and required models capable of producing enough plagioclase to build it. But gravity measurements from the Grail mission indicated that the crust is thinner than scientists once thought, making a deep magma ocean easier to reconcile with the amount of anorthosite actually present. Today, broad estimates place the crust at roughly 40 kilometers thick on the near side and around 60 kilometers on the far side, though the real structure varies by region. That difference is one of the moon's deepest geological puzzles. The hemisphere facing Earth carries a thinner crust, and much later would become the side where dark volcanic plains spread most widely. The far side developed a thicker, more elevated crust with far fewer large maria. NASA describes the near side crust as only about 2/3 as thick as the far side crust, but why the imbalance emerged is still unsettled. It may have begun during the Magma ocean era. Earth was then much closer in the lunar sky, enormous and radiating intense heat from its own molten aftermath. One possibility is that unequal heating delayed cooling on the near side, while allowing the far side to solidify more quickly, encouraging crust-building minerals to accumulate unevenly. Other models focus on the dynamics of the lunar interior, the distribution of heat-producing elements, or later giant impacts that may have modified an earlier difference. None has yet closed the case. The face in the night sky may preserve an asymmetry established while both worlds still glowed. As crystallization continued, the magma ocean changed composition. The minerals that formed early removed common elements from the melt, while substances that did not fit easily into their crystal structures became concentrated in the remaining liquid. These are called incompatible elements, not because they are unstable, but because the growing minerals tended to reject them. Near the final stages, the leftover melt became enriched in potassium, rare earth elements, and phosphorus, producing the chemical signature summarized by the name creep. It also carried uranium and thorium, whose radioactive decay released heat over long periods. Creep was not a global surface ocean painted across the moon. It was the concentrated residue of an immense crystallization process, a small late fraction that inherited many of the elements excluded from everything that formed before it. Classic lunar models place its origin after most of the magma ocean had crystallized, perhaps after roughly 95 to 99% of the original melt had become solid. This final liquid would later matter far beyond its volume. Because it contained heat-producing elements, regions rich in creep could remain warmer, melt more easily, and help fuel later magmatic activity. Much of the strongest known creep signal lies on the near side within a vast geochemical province associated with Oceanus Procellarum, raising an irresistible question. Did these elements help determine why the near side became so volcanically different from the far side? The answer is probably part of the story, though not the whole of it. Apollo astronauts landed within or near this unusual province, which means many of the rocks that first shaped scientific ideas about lunar evolution came from a region that may not represent the moon as a whole. Orbital mapping and lunar meteorites from more widely scattered locations have since revealed a more complicated crust than the early Apollo-based model suggested. Recent mission studies note that the global magma ocean model remains influential, but may not by itself explain every feature of the primitive moon. The uncertainty is not about whether the early moon experienced enormous melting. Evidence for that is strong. The harder question is how uniform the melting was, how long it lasted, how efficiently crystals separated from liquid, and how often the forming crust was broken and remade. Cooling time is especially difficult to pin down. A bare sphere of magma might seem as though it should freeze quickly in space, but a growing crust acts as insulation. Radioactive elements add internal heat. Impacts deliver new energy. Tidal forces from the nearby Earth may also have stirred and warmed the young moon. Depending on the model and on what event a sample records, estimates for the magma ocean's lifetime range from relatively short intervals to tens or even hundreds of millions of years. NASA summarizes the evidence as consistent with a deep magma ocean lasting tens to hundreds of millions of years, while newer zircon analyses have been interpreted to mean that the main ocean may have become almost completely solid much earlier than some older models proposed. These views may partly reflect different definitions of finished. Most of the moon could have solidified while isolated pockets of melt remained trapped below the crust. A nearly frozen interior is not the same as a geologically inactive one. The final 1% of a magma system can be disproportionately important because it carries concentrated heat-producing elements and chemically unusual material. As the mantle formed, it may also have become gravitationally unstable. Some minerals crystallizing late were rich in iron and titanium, making upper layers denser than material beneath them. Dense material may have sunk while lighter mantle rose, creating a process known as mantle overturn. If it occurred as models suggest, the Moon's interior reorganized after its first apparent layering, carrying heat-producing material downward in some places and helping generate later melting in others. The first crust was therefore not the final crust, and the first mantle was not necessarily left in its original order. The Moon was still remaking itself from within, even as its surface darkened and its glow faded into reflected sunlight. By around 4.4 billion years ago, ancient anorthositic crust had begun to survive long enough to leave a record, though almost none of that record remains untouched. The oldest recognizable landscape was about to face a new force, debris still moving through the young solar system. Asteroids and leftover planetary building blocks would strike the fragile shell, punching through it, melting it, mixing deep and shallow rocks, and erasing large sections of the first surface. The pale crust rising from the magma ocean had given the Moon its earliest face, but the face visible today would be carved by violence from above. The first solid landscapes of the Moon did not remain untouched for long. Across the young solar system, countless objects still traveled on unstable paths. Asteroids, planetesimals, fragments of failed worlds, and debris left behind from the violent process of planetary formation. The Moon stood directly in their path, and unlike Earth, it had no thick atmosphere to slow incoming bodies, no oceans to absorb their energy, and no active crust capable of erasing the damage afterward. Each impact arrived at enormous speed. A rock only a few kilometers wide could strike with enough force to excavate a cavity many times larger than itself, vaporizing part of the surface, melting deeper layers, and throwing curtains of debris hundreds of kilometers across the surrounding terrain. On the airless Moon, there was no sound, no shockwave rolling through a sky, and no fire burning in oxygen. The event would have unfolded in absolute silence, yet the ground itself would have convulsed as though the entire world had been struck like a bell. The circular scars covering the Moon are the frozen remains of this long age of bombardment, and they reveal something Earth can no longer show us clearly: what the inner solar system looked like when collisions were not rare disasters, but one of the main forces shaping worlds. A lunar crater begins in a fraction of a second. The incoming object compresses itself and the surface beneath it so violently that both behave less like solid rock and more like fluid under extreme pressure. A shockwave races downward and outward, crushing minerals and heating them beyond their normal melting points. Material is then driven away from the impact site, forming an expanding cavity. In a small crater, the walls eventually settle into a relatively simple bowl. In a larger one, gravity pulls the unstable walls inward, terraces collapse, and the compressed floor rebounds upward to form a central peak. Still larger impacts can produce rings of mountains, enormous fractured basins, and networks of faults extending deep into the crust. This is why the Moon's surface contains more than random holes. It carries a hierarchy of destruction, from tiny pits in individual rocks to basins so vast they reshape an entire hemisphere. One of the largest known is the South Pole Aitken Basin on the far side, a structure roughly 2,500 kilometers across and several kilometers deep. It is so immense that standing inside it would not feel like standing in a crater. Its rim would lie far beyond the horizon, and the curvature of the moon would hide the full scale of the feature. The impact that formed it may have penetrated deeply enough to expose or excavate material from the lower crust and perhaps the upper mantle, making the basin one of the most scientifically valuable regions on the moon. Yet even its exact age and formation details remain subjects of investigation, because the oldest lunar surfaces have been struck so many times that later impacts partially erased the evidence of earlier ones. The moon's history is not written in clean pages. It is written on a surface that has been repeatedly damaged, overwritten, and mixed. On Earth, large impact scars are difficult to preserve. Wind rounds their edges, rivers cut through them, sediments bury them, volcanoes cover them. Tectonic plates drag pieces of ancient crust into the mantle, where the rock is melted and recycled. The oldest parts of Earth have therefore lost much of the record of the violent environment in which the planet formed. The Moon, by contrast, has no rain, no flowing rivers, no forests, and no plate tectonics operating on a global scale. Its surface still changes, but slowly. Micrometeorites grind rocks into dust. Temperature swings fracture exposed material. New impacts disturb old terrain. Moonquakes shift slopes, yet these processes are far less efficient at erasing ancient structures than the geological systems active on Earth. As a result, the Moon functions like a battered archive left outside time. By reading its craters, scientists can infer not only what happened to the Moon, but what likely happened to Earth, Mars, Mercury, and Venus during the same era. The most heavily cratered regions are generally the oldest because they have been exposed to impacts for the longest time. Younger surfaces contain fewer craters because they formed after much of the early debris had already been cleared from the solar system. This basic relationship allows planetary scientists to estimate relative ages by crater counting. If two terrains lie beside each other and one is densely marked while the other appears smoother, the smoother surface is usually younger. The method sounds simple until it is applied to real landscapes. Small impacts can erase earlier small craters. Ejecta from a large collision can bury surrounding terrain and create thousands of secondary craters when falling blocks strike the ground. Different sizes of impactors were more common during different periods. A single image may therefore contain several overlapping generations of destruction, and each generation must be separated before the surface can be dated with confidence. Absolute ages require samples that can be analyzed in laboratories on Earth. Rocks collected by Apollo missions provided dates for several important regions, and those dates became anchor points for crater counting models used across the solar system. When scientists estimate the age of an unvisited plain on Mars or Mercury by studying its craters, part of that calculation ultimately depends on rocks carried home from the Moon. Yet the lunar samples created a mystery of their own. Many impact melt rocks from different Apollo landing sites appeared to cluster around an age of roughly 3.9 billion years. This pattern inspired the idea of a late heavy bombardment, sometimes called the lunar cataclysm, a sudden spike in impacts hundreds of millions of years after the planets first formed. In one influential version of the hypothesis, the giant planets changed their orbits, destabilizing reservoirs of asteroids and comets and sending a wave of objects toward the inner solar system. The Moon, Earth, and neighboring planets would then have endured an intense but relatively brief assault. It is a powerful idea because it links lunar geology to the architecture of the entire solar system. But the evidence is not as straightforward as the dramatic name suggests. Apollo missions landed within a limited region on the near side, much of it influenced by ejecta from the enormous Imbrium impact. Some rocks, originally thought to represent separate basins, may instead have been fragments of the same event, scattered across distant landing sites. If so, The apparent clustering near 3.9 billion years may partly reflect where astronauts collected samples rather than a true solar system-wide catastrophe. Other models propose that the impact rate declined gradually but unevenly, with several large collisions occurring late enough to dominate the surviving rock record. The question is no longer simply whether the early moon was heavily bombarded, it clearly was, but whether that bombardment included one sudden exceptional surge or a more complicated decline stretched across hundreds of millions of years. The distinction matters because Earth was present during the same period. If the moon experienced a sharp cataclysm, Earth may have been struck repeatedly just as its earliest oceans and perhaps its earliest life were emerging. Some impacts would have devastated regional environments, vaporized large volumes of water, and heated the atmosphere. Yet impacts could also have delivered water, carbon compounds, and other materials important to prebiotic chemistry. The same process capable of destroying fragile environments may also have contributed ingredients that later became useful to life. This does not mean bombardment created life, nor that life could not have arisen without it. It means the boundary between catastrophe and opportunity is not always clean when viewed across geological time. A collision that sterilized the surface locally might open hydrothermal systems below ground, where heated waters circulated through fractured rock and created new chemical environments. The lunar craters cannot tell us exactly how life responded on Earth, but they preserve the timing and scale of the dangers surrounding it. Among the moon's most dramatic structures are the great multi-ring basins. Imbrium, Serenitatis, Chrysium, Nectaris, and Orientale were created by impacts far beyond anything witnessed in human history. Their formation excavated deep crust, raised mountain rings, fractured the surrounding landscape, and covered enormous areas with ejecta. The Oriental Basin, near the western edge of the visible moon, is especially striking because its rings remain unusually well preserved. Seen from orbit, it resembles a target carved into a planet, concentric ridges hundreds of kilometers wide surrounding a partly flooded interior. It may represent one of the clearest examples of how a large planetary basin forms, though even here scientists debate exactly how the rings developed. Some may have arisen from collapsing walls, while others may reflect deeper faults formed as the crust adjusted after the impact. The scale of these events is difficult to grasp because the resulting landscape appears static today. A basin now seen as a graceful circular pattern began as a region where rock was compressed, liquefied, ejected, and rearranged in minutes. Mountains rose not through slow tectonic uplift, but through the immediate response of a shattered crust. Vast sheets of debris swept outward, burying older terrain and resetting the geological clock over areas the size of countries. The impacts also left weaknesses deep below the surface. Fractures produced by basin formation later became pathways through which molten rock could rise, helping prepare the dark volcanic plains that would fill some of these scars. In this way, bombardment did not merely decorate the moon with craters. It reorganized the crust and influenced geological activity long after the collisions themselves had ended. Even the smallest marks are part of the same continuing process. The lunar surface is constantly struck by tiny particles moving at high speed. Over billions of years, these micrometeorites have shattered exposed rock into regolith, the loose layer of dust, glass fragments, and broken minerals covering much of the moon. Individual grains can contain material melted by impacts, particles implanted by the solar wind, and fragments thrown from distant craters. A handful of lunar soil is therefore not simply dirt. It is a mixture assembled by countless collisions, each grain carrying part of a history that may have begun far from where it was collected. Some fragments could even have originated on Earth, blasted into space by ancient impacts and eventually deposited on the Moon, where they might preserve traces of an early terrestrial crust long since erased at home. Researchers have identified possible examples, but proving their origin is extremely difficult because impact processes can alter rock chemistry and because lunar material itself is so varied. Still, the possibility transforms the Moon from a record of its own past into a potential vault containing lost pieces of Earth. There is also a visual deception in the cratered landscape. From a distance, every scar appears permanent, but the surface is an active palimpsest. New craters overlap older ones, sunlight changes their apparent depth. Landslides soften steep walls. Ejecta rays fade under continued micrometeorite impacts. Some relatively young craters, such as Tycho and Copernicus, display bright ray systems stretching across the surface, while older structures have lost much of that contrast. The rays are not beams of light or cracks in the ground. They are trails of excavated material thrown outward during impact. Over time, space weathering darkens them until they become harder to distinguish. This slow fading gives planetary scientists another clue to relative age, but it also reminds us that the Moon is not truly frozen. It is changing at a pace so slow that a human lifetime barely registers. The bombardment that built its most famous features has greatly diminished, yet it has never completely stopped. New craters still appear. Future impacts will eventually damage landing sites, alter familiar formations, and erase some of the oldest evidence. For now, however, the giant scars remain, preserving a chapter of solar system history that Earth could not keep. Beneath several of those ancient basins, fractures were already reaching toward warmer rock below. The age of impacts had broken the crust open, and through those wounds the Moon's interior was about to return to the surface. The Moon's great wounds did not remain empty. Beneath the fractured crust, heat left over from formation, radioactive decay, and the slow reorganization of the interior continued to generate pockets of molten rock. And in the aftermath of the largest impacts, those pockets found paths upward. What followed was not a single eruption, but a long volcanic era that transformed parts of the lunar surface over hundreds of millions of years. Through deep fractures beneath enormous basins, dark basaltic lava rose from the mantle and spilled across the crater floors, spreading in broad, glowing sheets that could travel great distances in the Moon's weak gravity. With no atmosphere to cool the surface rapidly through wind, and no water to break apart the rock, these flows hardened into vast plains of dense, dark basalt. Seen from Earth, they appeared smoother and darker than the surrounding highlands, so early observers gave them names such as Mare Imbrium, the Sea of Rains, Mare Serenitatis, the Sea of Serenity, and Mare Tranquillitatis, the Sea of Tranquility. They were never seas of water, but the name survived because imagination reached the Moon long before geology did. To the unaided eye, the dark plains looked calm, almost soft, yet their origins were anything but peaceful. Each one was built inside a basin created by violence, then filled by eruptions that remade the landscape from below. The largest flows may have covered thousands of square kilometers, burying older craters, surrounding mountain peaks, and creating new surfaces that looked young compared with the ancient highlands around them. In places, only the tops of older structures remained visible above the basalt, like islands rising from a frozen black ocean. The lava was rich in iron and magnesium, which gave it a lower reflectivity than the pale anorthositic crust. That contrast created the pattern humans still recognize as the face of the Moon. Yet the Maria cover only a minority of the lunar surface. and most of them lie on the side facing Earth. This uneven distribution is one of the clearest signs that the Moon did not cool in a simple symmetrical way. The near side contains broad volcanic plains, thinner crust, and a high concentration of heat-producing elements in and around a region known as the Procellarum creep terrain. The far side, by contrast, is dominated by thicker crust and heavily cratered highlands, with relatively little widespread basalt. The difference is so dramatic that the first images of the far side surprised scientists. Instead of another familiar face filled with dark seas, spacecraft revealed a rougher, brighter hemisphere, crowded with impact scars and lacking the broad volcanic expanses visible from Earth. The simplest explanation is that lava reached the surface more easily where the crust was thinner, but that only moves the mystery one step backward. Why was the crust thinner on the near side in the first place? Why were so many radioactive elements concentrated there? Why did volcanic activity persist longer in some regions than in others? One possibility is that the young Earth, then much hotter and much closer in the lunar sky, slowed cooling on the near side, while the far side radiated heat more efficiently into space. Another possibility is that internal convection distributed heat unevenly from the beginning. Some models suggest that material rich in potassium, thorium, uranium, and other heat-producing elements became concentrated beneath the near side, creating a long-lived thermal reservoir that encouraged later melting. Still other explanations involve the effects of giant impacts, which may have thinned the crust locally and triggered mantle upwelling. The final pattern may have resulted from several of these processes acting together rather than from a single cause. This is often how planetary history works. A feature visible in one glance can require a chain of events spanning hundreds of millions of years to explain. The timing of lunar volcanism also reveals a world that remained active much longer than its size might suggest. Most large mare basalts formed between roughly 3.9 and 3.1 billion years ago, when the interior still held enough heat to generate substantial melt. Some eruptions continued much later, and certain volcanic deposits may be less than 2 billion years old. Observations of small, irregular patches, known as irregular mare patches, have even raised the possibility of geologically recent activity, perhaps within the last 100 million years in a few locations, though their exact origin and age remain debated. If some of these features truly are that young, they would challenge the traditional picture of a moon that became completely inactive early in its history. They would not mean that lava is flowing there today, but they would suggest that isolated pockets of melt survived far longer than once expected. The moon's small size allowed heat to escape more quickly than on Earth, yet it did not cool everywhere at the same rate. A planet or moon is not a single furnace turning off. It is a complex body in which radioactive elements, crustal thickness, chemical composition, and pressure create regions with different thermal histories. The near side may have remained geologically restless, while the far side had already entered a deeper silence. Evidence for that restlessness survives in structures that are easy to overlook. Winding channels called sinuous rills cut across some maria, resembling dried riverbeds when seen from orbit. But no rivers carved them. Many were formed by flowing lava, either as open channels or as tubes whose roofs later collapsed. Rima Hadley, visited by Apollo 15 astronauts, extends for more than 100 kilometers and reaches hundreds of meters in depth. Standing beside it, the astronauts were not looking at erosion by water, but at the path of an ancient molten current. Elsewhere, lava tubes may remain intact beneath the surface, forming long caves protected from radiation, temperature extremes, and micrometeorite impacts. These hidden spaces have become especially interesting for future exploration, because they could provide natural shelter for equipment or human crews. Their existence also changes the emotional scale of the Moon. What appears flat and exposed from Earth may contain enormous underground passages formed when flowing lava hardened on the outside but continued moving beneath a solid roof. When the eruption ended, the empty conduit remained, a hollow memory of heat sealed inside a frozen world. Volcanic domes offer another clue. Some are low, broad structures formed by thicker lava that piled up near its source instead of traveling far. Others contain vents or pits at their summits, marking places where gases and magma once escaped. Dark deposits around certain vents suggest explosive eruptions, which may seem surprising on an airless body. Lunar magma could contain dissolved gases such as carbon monoxide, sulfur compounds, or water-related molecules. As pressure dropped near the surface, those gases expanded and fragmented the magma, throwing fine volcanic glass over the surrounding terrain. Apollo astronauts collected orange and green glass beads created by such fire fountain eruptions. Under a microscope, those tiny spheres reveal that the lunar mantle held more volatile material than early scientists assumed. The Moon was still extremely dry compared with Earth, but not completely emptied of every gas or trace of water. Some beads contain chemical clues to material that rose from deep inside, allowing scientists to study regions of the mantle that no drill has ever reached. In this sense, volcanic eruptions became messengers, carrying fragments of the hidden Moon to the surface. The basalts themselves also vary. Some contain unusually high concentrations of titanium, while others contain very little. These chemical differences indicate that the mantle was not uniform. It had been layered, overturned, mixed, and partially melted in ways shaped by the Moon's earliest crystallization. When scientists compare basalt samples from different landing sites, they are not simply studying separate eruptions. They are sampling different portions of an interior that had already experienced billions of years of change. Each lava flow is a partial answer to the question of how the Moon cooled, but no single sample can represent the entire world. The Apollo missions landed mostly within a limited region on the near side, and although their samples transformed lunar science, they also created a geographical bias. Later robotic missions and lunar meteorites have helped broaden the picture, yet enormous areas remain unsampled. The far side, the poles, and the floor of the South Pole Aitken Basin may contain rocks capable of revising the volcanic timeline again. This is why the Moon can look familiar while remaining scientifically incomplete. We have mapped nearly every visible ridge, but we have physically examined only a tiny fraction of its surface. As volcanic activity declined, the Maria began accumulating their own craters, allowing scientists to distinguish older flows from younger ones. A dark plain with many overlapping craters had been exposed longer than a smoother neighboring flow. In some regions, separate eruptions can be traced as distinct layers or boundaries, showing that a single mare may have been built through many episodes, rather than one vast flood. Lava returned repeatedly, sometimes separated by millions of years, covering earlier surfaces and creating a geological record stacked horizontally across the basin. The apparent simplicity of a dark patch seen from Earth hides this complexity. What looks like one sea may actually contain dozens of flows, each produced by changing conditions below. Eventually, however, the eruptions became less frequent. The interior lost heat. Melt was harder to generate, and the thickening lithosphere made it more difficult for magma to reach the surface. Yet cooling introduced new kinds of motion. As the Moon's interior contracted, the crust was compressed, forming curved cliffs known as lobate scarps. Some of these scarps cut across relatively young craters, suggesting that they formed recently in geological terms and may still be developing. The Moon has shrunk by tens of meters in diameter as it cooled, wrinkling its outer shell like the skin of a drying fruit, though on a far larger scale. Instruments placed by Apollo missions also detected moonquakes. Some originated deep within the interior and followed monthly patterns influenced by Earth's tidal pull. Others were shallow, less frequent, and sometimes stronger. Thermal moonquakes occurred as the surface expanded and contracted during the extreme transition between lunar day and night. Meteorite impacts created additional vibrations. The Moon is therefore not seismically dead. It trembles, contracts, fractures, and responds to the gravity of Earth, even though its activity is far quieter than Earth's. Because the lunar interior is dry and rigid, seismic waves can continue reverberating for a long time, giving rise to the old description that the Moon rang like a bell. The phrase is dramatic, but it reflects a real difference in how vibrations move through fractured, low-moisture rock. This lingering motion reveals a world that is not alive in the terrestrial sense, yet not completely still. Its greatest volcanic era has ended, but the process of cooling continues. Beneath the dark plains, ancient lava remains locked in place. Above them, impact debris slowly turns stone into dust. Along young faults, the crust adjusts by small degrees to an interior still losing heat after more than 4 billion years. And all the while, another force has been working without interruption, powerful enough to move entire oceans on Earth and subtle enough to stretch the distance between two worlds. The Moon's fire was fading, but its gravitational influence was only beginning to reveal how deeply one silent world could reshape another. The Moon has been slowing Earth down for more than 4 billion years, not by touching it, not by pushing against its surface, but by pulling continuously on a planet that refuses to stop turning. The effect is so gradual that no person can feel it, yet it has altered the length of every day, changed the distance between the two worlds, reshaped coastlines through tides, and quietly redirected the mechanical future of the Earth-Moon system. To understand how, it helps to begin not with the modern ocean, but with a much younger Earth spinning far faster than it does now. A day may once have lasted only a fraction of its present 24 hours, though the exact length depends on which stage of early history is being modeled. The Moon was also much closer, appearing larger in the sky and exerting a stronger tidal influence. Earth and Moon were already bound together, but their relationship was not static. From the beginning, they were exchanging energy and angular momentum, and that exchange has never stopped. The visible expression of this process is the tide. It is often described as the Moon pulling the ocean toward itself, which is partly true but incomplete. The more accurate explanation lies in the difference between the Moon's gravitational pull on the near side of Earth, the center of Earth, and the far side. The side facing the Moon is pulled slightly more strongly than Earth's center, while the far side is pulled slightly less strongly. Those differences stretch the planet along the Earth-Moon line, producing two broad tidal bulges rather than one. One forms roughly on the side facing the Moon, and another forms on the opposite side. The solid Earth is distorted as well, though much less visibly than the oceans. Even the atmosphere responds. What we call the ocean tide is therefore part of a planetary deformation, a repeated stretching of Earth under an uneven gravitational field. If Earth were perfectly smooth, completely covered by an ocean of uniform depth, and rotating without continents, the pattern might seem simple. Real tides are not. Continents block the movement of water. Ocean basins have different shapes and depths. Coastlines focus tidal energy into narrow bays. The Coriolis effect bends moving water, while resonance can amplify tides in some regions and weaken them in others. This is why the timing and height of tides vary dramatically across the world. Some coastlines experience only modest changes, while places such as the Bay of Fundy can experience enormous tidal ranges. The moon provides the dominant gravitational rhythm, but the geography of Earth writes the local version of the song. The sun also raises tides. Although it is vastly more massive than the moon, it is much farther away, and tidal effects depend strongly on changes in gravity across Earth rather than on gravity alone. The sun's tidal influence is therefore weaker than the moon's, but still significant. When the sun, moon, and Earth align near a new moon or full moon, their tidal effects reinforce one another, producing spring tides, a term related to the water springing higher rather than to the season. Near the first and third quarter moons, the solar and lunar tidal forces partly oppose one another, producing smaller neap tides. These cycles were visible to coastal peoples long before anyone understood the mathematics behind them. But beneath the rising and falling water lies a deeper process. Earth rotates once in about 24 hours, while the moon takes much longer to complete an orbit. Because Earth turns faster than the moon moves around it, the tidal bulges are carried slightly ahead of the line directly connecting Earth and moon. Friction between the oceans and the sea floor, along with the complicated movement of water through basins and around continents, prevents the bulges from remaining perfectly aligned. That small offset changes everything. The bulge nearer the moon exerts a gravitational pull on the moon that is angled slightly forward along its orbit. In effect, Earth's rotation gives the moon a tiny gravitational boost. The moon gains orbital angular momentum and moves into a slightly wider orbit. At the same time, Earth loses rotational angular momentum and spins slightly more slowly. No momentum disappears. It is transferred from the turning Earth to the orbiting moon, while some rotational energy is converted into heat through tidal friction. The oceans do not merely rise and fall. They are part of a planetary braking system. At present, the length of Earth's day increases on average by roughly a couple of milliseconds per century, though the exact rate varies over time. The moon is moving away from Earth by about 3.8 centimeters per year, a value measured with remarkable precision using laser reflectors placed on the lunar surface during the Apollo missions and by Soviet robotic missions. Observatories on Earth fire laser pulses toward these reflectors and measure how long the light takes to return. The distance can be determined with extraordinary accuracy, revealing that the gap between the worlds grows by an amount roughly comparable to the growth of a fingernail each year. That sounds insignificant until time is allowed to accumulate. Over millions and billions of years, centimeters become thousands of kilometers, and milliseconds become hours. The present recession rate, however, cannot simply be projected backward at a constant value. If the moon had always moved away at exactly 3.8 centimeters per year, some calculations would place it impossibly close to Earth far later than its accepted formation time. The reason is that tidal evolution depends on Earth's changing geography. Continents drift, ocean basins open and close, sea levels change. The efficiency with which tides lose energy changes as coastlines and seafloors are rearranged. At certain times, an ocean basin can approach resonance, allowing tidal waves to build more strongly and increasing the transfer of angular momentum. At other times, the arrangement of continents may make tidal dissipation weaker. The modern rate is therefore a snapshot, not a permanent constant. Ancient sediments offer another way to reconstruct this changing rhythm. In some tidal environments, layers of sand and mud were deposited in patterns linked to daily, monthly, and seasonal cycles. These tidal rhythmites can preserve repeated bands like a geological calendar. By counting and comparing them, researchers can estimate how many days existed in an ancient month or year. Fossil corals and shells can also record growth bands associated with daily and yearly cycles. Such evidence suggests that hundreds of millions of years ago, Earth had more days in each year because each day was shorter. The year itself was not dramatically shorter. Earth was simply completing more rotations during one orbit around the Sun. Around 400 million years ago, a day may have lasted roughly 22 hours, though estimates vary depending on the evidence and interpretation. Go much farther back and the uncertainties grow, but the overall direction remains clear. Earth once turned faster. The familiar 24-hour day is not a fixed property of the universe. It is the current stage of a long gravitational negotiation. This slowing has affected more than clocks. A faster spinning Earth would have produced different atmospheric circulation, stronger rotational effects on winds and oceans, and a different relationship between daylight and nighttime cooling. Shorter days would have changed the frequency of temperature cycles experienced by early environments, though it would be too simple to claim that one day length was inherently better for life than another. Organisms adapt to the rhythms available to them. What matters is that the rhythm itself has been changing throughout biological history. Every species that uses a daily cycle has evolved on a planet whose rotation was being gradually altered by the moon. The moon underwent an even more dramatic transformation. Tidal forces raised distortions in the moon, just as the moon raised tides on Earth. Early in its history, the moon probably rotated faster than it does today. Internal friction caused by repeated tidal flexing dissipated energy and slowed that rotation until the moon entered synchronous rotation, completing one turn on its axis in the same time it takes to orbit Earth. This is why nearly the same lunar hemisphere always faces us. The moon is not failing to rotate. It rotates exactly once per orbit. That state is called tidal locking, and it is common among moons throughout the solar system. Earth is not currently tidally locked to the moon because its greater mass and faster rotation make the process much slower. But the system continues moving in that general direction. In an extremely distant theoretical future, if the Sun and other changes did not intervene first, Earth's rotation could slow until one side of Earth always faced the moon, while the moon completed a much wider orbit over the same period. Both worlds would then be mutually locked. In reality, the Sun's evolution will radically transform the system long before such a simple final state is reached. So this outcome is more useful as a mechanical limit than a literal forecast. The moon's outward migration also changes the appearance of eclipses. Today, the Sun is about 400 times wider than the moon, but also about 400 times farther away, allowing their apparent sizes in our sky to be remarkably similar. That coincidence makes total solar eclipses possible, during which the moon can cover the Sun's bright surface while revealing the faint corona around it. Because the moon is gradually moving farther away, its apparent size is slowly shrinking. In the distant future, total eclipses will become less common and eventually cease, replaced by annular eclipses in which a bright ring of sunlight remains visible around the smaller lunar disk. There is no single exact date because the moon's recession rate changes and both lunar and terrestrial orbits vary, but the broad outcome follows directly from the widening distance. The age of perfect totality is temporary. We happen to live during one interval when the geometry aligns closely enough to create one of nature's most dramatic sights. Yet the same gravitational machinery that makes those eclipses possible is slowly removing them. The transfer of momentum also carries an important lesson about how a planet can change without a visible catastrophe. Impact craters, eruptions, and earthquakes announce themselves through sudden destruction. Tidal evolution works through repetition. One ocean crossing a continental shelf does almost nothing to Earth's rotation. Billions of tides do. Each cycle dissipates a small amount of energy as water flows through straits, drags across the seafloor, and breaks against coastlines. The effect is almost immeasurable from one day to the next, but geological time turns weakness into power. The moon's influence is therefore not best understood as a single force acting once. It is persistence made physical. A pull too gentle to notice in an ordinary moment has lengthened the day, widened in orbit, synchronized the moon's rotation, and shaped the timing of coastlines across the planet. Even now, every high tide contains a trace of Earth's lost rotational energy. Every laser measurement to the moon confirms that the two worlds are separating. Every 24-hour day is only a temporary point between a faster past and a slower future. The moon has not merely traveled beside Earth through time. It has changed the rate at which Earth itself experiences time. And if its gravitational pull can reshape rotation and move oceans across entire basins, the next question becomes even larger. How much has that same companion influenced the long-term stability of the planet on which life emerged? The moon is often described as Earth's stabilizing anchor, a phrase so elegant that it can easily sound more certain than the science allows. The idea is not wrong, but the real relationship is more subtle and far more interesting. Earth does not spin perfectly upright. Its axis is tilted by about 23.4 degrees relative to the plane of its orbit around the Sun, and that tilt is what gives the planet its seasons. As Earth travels around the Sun, first one hemisphere leans more directly toward the light, then the other. Without that tilt, seasonal differences would be much weaker across much of the planet. With a much larger or rapidly changing tilt, seasons could become more extreme, moving heat, ice, rain, and habitable environments across the globe in unfamiliar ways. The moon matters because its gravitational pull influences how Earth's rotational axis moves through time. Earth behaves somewhat like a spinning top. Its axis slowly traces a circle in space through a motion called precession, completing one cycle over roughly 26,000 years. The moon contributes strongly to the rate of that motion. By making Earth's axis precess relatively quickly, it can help prevent certain gravitational interactions with other planets from pushing the tilt into more chaotic variations. Computer models have suggested that without a large moon, Earth's obliquity might wander through a wider range over millions of years, potentially producing more dramatic climate shifts. That conclusion helped create the popular image of the moon as a guardian keeping Earth steady. Yet, this should not be turned into the claim that a moonless Earth would tumble randomly or become immediately uninhabitable. Later studies have shown that the outcome depends on the starting conditions, the architecture of the solar system, the speed of Earth's rotation, and the time interval being considered. A moonless Earth could still retain a moderate tilt for long periods under some scenarios. Its climate might be more variable, but variable does not automatically mean lifeless. Mars offers a useful comparison, though not a perfect one. It lacks a large, stabilizing moon, and its axial tilt has changed far more dramatically over geological time, shifting the distribution of sunlight and perhaps moving ice between the poles and lower latitudes. But Mars is also smaller than Earth, has a different orbit, a thinner atmosphere, and a completely different geological history. Its instability cannot be blamed on the absence of a large moon alone. The most responsible scientific view is that the Moon probably reduces the range and complexity of Earth's long-term axial variations, but exactly how essential that stability has been for life remains uncertain. This uncertainty leads into one of the most tempting questions in planetary science. Did the Moon help make Earth alive? The safest answer is that no evidence proves life required the Moon. Microbial life may be able to emerge and survive under conditions far more varied than those experienced on modern Earth. A world without a large satellite might still possess liquid water, chemistry rich in carbon, internal heat, and stable environments lasting long enough for biology to begin. But the Moon did shape the world on which life actually appeared, and that distinction matters. Life does not evolve on an abstract planet built from minimum requirements. It evolves inside a specific history of tides, daylight, seasons, coastlines, impacts, and changing environments. The Moon was woven into that history from the start. Its earliest influence would have been much stronger than it is now because it orbited closer to Earth. Tides may have been larger and more frequent, sweeping water repeatedly across young coastlines. The exact appearance of those coastlines is uncertain because Earth's crust was still evolving and the continents familiar today did not exist. But anywhere shallow water met exposed rock, cycles of flooding and drying could have created chemically unusual environments. Some origin of life hypotheses propose that repeated wet-dry cycles helped simple organic molecules link into longer chains. In water, certain chemical bonds are difficult to form because the surrounding water favors their breakdown. As a pool dries, molecules become concentrated, temperatures change, minerals interact with them, and reactions that were unlikely in a large open ocean may become easier. When water returns, the products can be dispersed, mixed, and subjected to another cycle. Tides are not the only way to create such conditions. Seasonal ponds, volcanic fields, hot springs, and rainfall could also produce repeated hydration and dehydration. Nor is there agreement that life began on land. Another major family of hypotheses places its origin near hydrothermal vents on the seafloor, where warm, mineral-rich fluids provide chemical gradients and protected spaces. The Moon cannot be declared the missing key in this debate. At most, powerful ancient tides may have increased the number and variety of environments in which prebiotic chemistry could proceed. They may have offered one path among several, and the oldest direct evidence of life is too incomplete to tell us which path was actually taken. The Moon may also have influenced the movement of nutrients. Tides stir shallow seas, mix oxygenated and deeper waters, transport sediments, and create zones that alternate between aquatic and exposed conditions. Long before complex animals appeared, microbial communities living in coastal environments would have experienced these rhythms. Later, when life expanded into tidal flats and shorelines, the boundary between sea and land became one of evolution's most demanding laboratories. An organism in the intertidal zone must tolerate immersion, exposure, changing temperature, changing salinity, waves, predators, and periods of reduced oxygen. These stresses can eliminate fragile forms, but they also reward flexibility. It would be too strong to say tides drove life onto land, because the transition involved plants, fungi, arthropods, vertebrates, changing atmospheres, and many ecological pressures. Still, tidal environments created repeated opportunities for organisms to survive brief periods out of water before any lineage became fully terrestrial. The Moon did not guide evolution toward a destination, but it helped shape one of the borders evolution repeatedly crossed. Its influence continued after life had become complex. Many marine species synchronize parts of their behavior with lunar or tidal cycles. Corals can release eggs and sperm in coordinated spawning events connected to seasonal conditions and the lunar phase. Grunion come onto beaches to lay eggs during particular tides. Certain worms, fish, Crustaceans and plankton adjust reproduction, feeding, migration, or emergence according to moonlight or changes in water level. For these organisms, the moon is not a distant object. It is part of the timing system embedded in their biology. The relationship is rarely controlled by moonlight alone. Temperature, food, tides, weather, and internal biological clocks all interact, and different species respond in different ways. Yet natural selection can use any reliable cycle. If a predictable lunar rhythm improves the chance of finding mates, avoiding predators, or placing offspring in favorable conditions, organisms that respond to it can gain an advantage. The result is a planet where events in orbit become encoded in genes, hormones, and behavior. Moonlight itself creates another ecological landscape. A full moon can transform a dark night into a period of increased visibility, but that visibility is not equally useful to every creature. Predators that hunt by sight may become more effective, while prey species may reduce their activity or seek heavier cover. Some nocturnal animals feed less under bright moonlight. Others take advantage of it. Tiny organisms moving vertically through the ocean may respond to lunar illumination, altering when they rise toward the surface. The moon therefore changes not only what animals can see, but the balance of risk across entire food webs. Human observers once treated the idea of lunar effects on behavior as a mixture of folklore and speculation, and many dramatic claims, especially claims that the full moon reliably causes madness, crime, or unusual births, have not held up consistently under careful statistical study. But rejecting exaggerated human myths does not erase the genuine biological effects found in species whose environments are directly shaped by tides and night brightness. The scientific challenge is to separate mechanisms from stories. A crab responding to water levels is not evidence that the moon secretly governs every mind, but it is evidence that celestial cycles can become biological signals. Even biological timekeeping may carry traces of these layered rhythms. Most organisms possess circadian clocks tuned roughly to the day-night cycle, but some coastal species also show circadian rhythms close to the interval between successive tides, while others display monthly patterns linked to the lunar cycle. These clocks can continue temporarily even when the external cue is removed, suggesting that evolution has built an expectation of the moon's rhythm into the organism itself. The remarkable point is not mystical influence, but physical predictability. Gravity moves water. Reflected sunlight changes darkness. Organisms respond. Across enough generations, response becomes adaptation. The moon also affects climate in less direct ways, through tides that mix the oceans. Tidal energy contributes to the movement of water across underwater ridges, continental shelves, and the deep sea floor, helping mix warmer and colder layers. Ocean circulation is driven mainly by winds, differences in temperature and salinity, Earth's rotation, and the shape of the basins, but tidal mixing is part of the system. Changes in the moon's distance, Earth's rotation, and the arrangement of continents would have altered where and how strongly that energy was dissipated. This does not mean the moon controls climate, but it participates in a network where seemingly small influences can matter over long periods. Climate stability itself is also more complicated than constancy. A perfectly unchanging world might not be ideal for evolution. Environmental change creates extinctions, but it also opens ecological space and drives adaptation. Ice ages, shifting shorelines, atmospheric changes, and continental drift have repeatedly disrupted life while creating new opportunities. If the moon reduced the most extreme swings in Earth's axial tilt, it may have kept climate changes within a range that allowed oceans and large habitable regions to persist. But too much stability is not obviously necessary, and some instability can increase diversity. The important point is not that the moon created a calm paradise. Earth has never been calm. The moon may instead have helped place certain variations inside boundaries that were survivable often enough for complexity to accumulate. There is another possibility hidden within the moon's origin itself. The collision associated with its formation may have changed Earth's chemistry, rotation, and internal structure. It may have removed part of an early atmosphere, mixed planetary material, or affected how Earth's metallic core and rocky mantle evolved. Some scientists have explored whether this event contributed to the conditions required for Earth's long-lived magnetic field or plate tectonics. But these links remain uncertain and should not be treated as established consequences. Earth's habitability emerged from many interacting features: its distance from the Sun, mass, water inventory, atmosphere, magnetic environment, internal heat, carbon cycle, and geological activity. The moon was one factor within that larger system, not a single explanation capable of replacing all the others. That may be the more profound view. Life did not appear because one perfect object performed one perfect function. It emerged on a world shaped by coincidences, constraints, disasters, and slow feedbacks. The moon helped regulate some motions, intensified others, illuminated nights, moved seas, and created rhythms that organisms learned to use. Whether life would have arisen without it remains an unanswered question because there is only one Earth available for comparison. We cannot remove the moon and replay 4 billion years. We can only build models, study other planets, examine ancient rocks, and search for living worlds around distant stars. Perhaps future observations will reveal Earth-like planets without large moons, showing that complex life does not require such a companion. Or perhaps large moons will prove unusually valuable, making stable, biologically rich planets rarer than expected. Until then, the moon should be understood neither as an accidental decoration nor as a guaranteed guardian. It is a participant in Earth's history, powerful in some ways, limited in others, and inseparable from the only example of life we know. Long before anyone measured its orbit, living things were already moving, feeding, hiding, and reproducing according to patterns written across the water and the night. Eventually, one species would look upward, recognize those patterns, and turn the moon from a biological rhythm into a measure of time, a source of myth, and the first world beyond Earth to enter human history. Before people could explain the moon, they learned to count with it. Long before mechanical clocks, printed calendars, or observatories, the changing shape of the moon offered something rare in the natural world, a cycle visible to almost everyone, repeating slowly enough to follow and regularly enough to trust. A thin crescent appeared after sunset, widened night by night, became full, then shrank into darkness before returning again. The cycle was not perfectly aligned with the seasons, and that imperfection would eventually create some of humanity's most complicated calendars, but to early communities, it provided a dependable structure inside an uncertain world. The moon turned darkness into sequence. One night was not simply followed by another. It belonged to a growing crescent, a brightening half, a full disk, or a fading arc. Time became something that could be watched. The interval from one new moon to the next is about 29.5 days, close enough to the human sense of a month that the connection appears in the very language many cultures use for time. Yet the lunar month is not an exact number of days, and 12 such cycles total only about 354 days, roughly 11 days shorter than the solar year. That difference seems small until it accumulates. A festival tied to 12 lunar months will gradually move through the seasons unless a calendar corrects the drift. After only a few years, an event once held in spring may arrive in winter. The moon gave humanity a clock, but not a simple one. It forced people to recognize that the heavens contain several overlapping rhythms: the day created by Earth's rotation, the lunar month, and the solar year. These cycles do not fit neatly together, and much of early astronomy grew from the effort to reconcile them. Some societies embraced calendars based mainly on lunar months, allowing important dates to move through the solar seasons. Others developed lunisolar systems, periodically adding an extra month so lunar phases remained connected to agriculture and the seasonal year. The decision was never purely mathematical. A calendar determined when taxes were collected, when crops were planted, when rulers announced ceremonies, when communities gathered, and when religious obligations began. To control the calendar was, in a real sense, to control the rhythm of public life. This is why ancient specialists who observed the sky were not merely curious stargazers. They served as timekeepers, advisors, ritual authorities, and interpreters of order. Their work linked events on Earth to patterns above it, giving political and spiritual meaning to astronomical prediction. The earliest possible records of lunar counting are difficult to interpret with certainty. Archaeologists have found notched bones, carved stones, and marked objects tens of thousands of years old, whose patterns may represent days or phases of the moon. Some researchers view these as primitive lunar calendars. Others caution that repeated marks can have many purposes, and that intention is almost impossible to prove across such distances of time. The ambiguity is important. Humanity probably noticed lunar cycles long before it left written explanations, but evidence of counting is not always evidence of astronomy. Still, by the time complex societies produced written records, lunar observation had clearly become systematic. In Mesopotamia, scribes tracked the first appearance of the crescent after sunset, using it to begin new months. This was not always easy. Clouds, dust, atmospheric haze, and the moon's position could delay visibility, so the start of a month depended partly on observation and judgment. Over centuries, increasingly detailed records allowed Babylonian astronomers to identify cycles, improve predictions, and connect lunar motion with eclipses. Their sky was not divided into modern categories of science and religion. An eclipse could be calculated as a celestial event and interpreted as a political warning at the same time. Prediction did not necessarily destroy meaning. It could increase the authority of those able to announce what the heavens would do. Egypt relied strongly on the solar year because the annual behavior of the Nile and the seasonal appearance of stars were central to agriculture. But lunar cycles still shaped rituals and religious time. In ancient Greece, city-states used lunar or lunisolar calendars that were not always synchronized with one another. Months might begin with the visible crescent, and extra months were inserted when necessary, sometimes with enough local variation to confuse anyone attempting to match dates across regions. The disorder reveals an important truth. Calendars are not discovered in nature fully assembled. Nature provides cycles. Societies decide how to organize them. A month can begin at the dark moon, the first visible crescent, or another chosen phase. A year can be corrected through observation, arithmetic, or political decree. Even when people look at the same moon, they do not automatically create the same system of time. In ancient China, careful lunar and solar observations became part of an elaborate state calendar. The ability to predict eclipses and regulate months was associated with the legitimacy of imperial rule, because cosmic order and political order were often understood as reflections of each other. Records preserved over many centuries now offer modern historians and astronomers valuable evidence about past eclipses, comets, and unusual celestial events. Similar traditions developed in India, where lunar days, phases, and constellations became essential to calendars, ritual timing, and mathematical astronomy. Indian astronomers produced increasingly precise models of celestial motion, while cultural systems integrated lunar timing into festivals and daily life. Across the Islamic world, the lunar calendar acquired a distinct religious importance. Months begin according to the lunar cycle, and significant observances move through the solar year because 12 lunar months are shorter than a tropical year. This movement means that fasting or pilgrimage can occur in different seasons over the course of a lifetime. The calendar does not attempt to keep the moon fixed to spring or harvest. Its seasonal drift is part of the system. Determining the beginning of a month has also produced long-standing discussions about physical crescent observation, local visibility, calculation, and the relationship between astronomical prediction and religious practice. These debates continue because the moon is both predictable in principle and sometimes difficult to see in practice. A mathematical conjunction does not guarantee that a young crescent will be visible from every location under real atmospheric conditions. The boundary between calculation and observation remains alive each time communities wait for the first thin arc after sunset. The Jewish calendar follows a different solution, combining lunar months with solar correction so religious festivals remain in their intended seasons. Extra months are inserted within a repeating 19-year pattern, an arrangement based on the near correspondence between 19 solar years and 235 lunar months. The cycle is not absolutely perfect, but it is accurate enough to coordinate two otherwise mismatched clocks over long periods. Variations of this 19-year relationship were recognized in several ancient traditions and are often associated in Greek history with Meton of Athens, though awareness of related cycles likely developed through broader and earlier exchanges of astronomical knowledge. The important insight was not the name attached to it, but the discovery that irregular-looking celestial motions could reveal longer patterns when observed patiently across generations. No individual could watch centuries pass, so astronomical knowledge depended on memory made collective, tablets, manuscripts, institutions, and records preserved by people who knew they would never live to see the full value of what they measured. The moon also guided people beyond formal calendars. Coastal communities watched its relationship with tides even when the physical cause was not understood. Fishers learned that certain phases and tidal conditions affected access to shallow waters, the movement of marine animals, and the safety of launching boats. Travelers used moonlight to extend movement into the night. Farmers sometimes organized tasks around traditional lunar rules, though claims that the moon reliably improves planting or harvesting outcomes are often difficult to separate from seasonal knowledge, local custom, and selective memory. What matters historically is that the moon provided a visible framework for decision-making. A full moon could illuminate roads, fields, and gatherings in a world without electric light. Military campaigns, religious processions, and long journeys might be planned around nights when the landscape remained visible after sunset. Darkness was not uniform throughout the month, and before modern lighting, that difference shaped human behavior far more strongly than it does for most people today. The full moon could turn a dangerous path into a usable one, while a moonless night could conceal both travelers and threats. Human beings did not merely count lunar phases, they experienced them physically. As the moon became part of organized time, it also became a screen for stories. People across the world looked at the same contrasts of dark basalt and pale highlands, but did not see the same image. In parts of Europe and later North America, observers commonly imagined a face or a man in the moon. In several East Asian and indigenous American traditions, the markings became a rabbit, sometimes connected with sacrifice, medicine, immortality, or transformation. Other cultures saw a woman, a frog, a tree, or figures carrying objects. These patterns were not evidence that ancient people misunderstood vision. They were examples of the mind doing what it always does, finding familiar forms in ambiguous shapes, and then using those forms to store cultural meaning. The moon's locked rotation ensured that nearly the same hemisphere faced Earth generation after generation, allowing the same markings to become a stable canvas for inherited stories. A child could be shown a figure in the moon that an ancestor had seen centuries earlier. The sky became a place where memory could be placed, beyond the reach of ordinary decay. Lunar deities reflected different aspects of that presence. The moon could be masculine in one culture and feminine in another, linked to fertility, hunting, wisdom, measurement, rebirth, or death. Its disappearance and return made it a natural symbol of renewal, yet its changing face could also suggest uncertainty or instability. The full moon represented completeness, while the fading crescent suggested loss. These meanings were not universal, and attempts to compress every lunar tradition into a single symbol usually reveal more about modern expectations than ancient belief. The moon was powerful precisely because it could support several interpretations at once. It changed but returned, vanished but remained predictable, illuminated the night yet belonged to darkness. Few natural objects offered such a convincing union of permanence and transformation. Eclipses intensified that tension. During a lunar eclipse, Earth passes between the sun and the moon enters Earth's shadow. It does not usually disappear completely. Instead, it may become copper, orange, or deep red because sunlight passing through Earth's atmosphere is filtered and bent into the shadow. Blue light is scattered more strongly, while redder wavelengths continue through, effectively coloring the moon with the light of every sunrise and sunset occurring around Earth's edge. The mechanism is beautiful, but before it was fully understood, the sight of the moon darkening could be deeply unsettling. Traditions describe celestial animals attacking it, divine displeasure, danger to rulers, or disruptions in cosmic order. Communities sometimes made noise, performed rituals, or offered prayers to protect or restore the moon. It is tempting to treat these responses as simple ignorance, but that overlooks the emotional logic of the event. The most regular object in the night sky suddenly appeared wounded. A source of time itself seemed to fail. Even when some astronomers could predict eclipses, most people experienced them not as equations, but as darkness unfolding across a familiar face. Prediction and fear could coexist. In Mesopotamian royal practice, an eclipse considered dangerous to the king might lead to protective rituals or even the temporary installation of a substitute king, reflecting a political system in which celestial events carried consequences for earthly authority. In China, failures to predict eclipses became part of historical accounts about court astronomers, although later retellings sometimes mixed fact and legend. Across cultures, the power to forecast an eclipse demonstrated that human reasoning could uncover order inside a terrifying event. That transition, from observing repetition to explaining mechanism, was one of the most important steps in intellectual history. The moon encouraged it because its motion was accessible enough to track but complicated enough to resist easy understanding. It rises at different times, moves against the background stars, changes phase, alters its apparent path through the seasons, and occasionally passes into shadow. To predict it accurately required geometry, arithmetic, record-keeping, and models of motion. Each improvement in lunar theory exposed errors in broader ideas about the cosmos. The moon was therefore not just humanity's first clock, it became one of humanity's first great scientific problems. Yet even the best ancient calendars had to confront the stubborn fact that celestial cycles do not divide evenly. Fractions accumulated, months drifted, observations disagreed with tables, authorities inserted corrections, and different communities defended different rules. Rather than making the moon a poor clock, these imperfections made it a demanding teacher. They showed that nature is orderly without being arranged for human convenience. The heavens repeat, but not according to simple whole numbers. Accurate timekeeping required patience with irregularity and the willingness to revise systems that seemed complete. By the early modern period, lunar tables would become essential for navigation, eclipse prediction, and the testing of gravitational theories. But before those advances, humanity had already spent millennia living inside lunar time. The moon determined when people gathered, fasted, traveled, planted, celebrated, and feared. It entered law, ritual, language, and memory so deeply that the modern month still carries the shadow of its cycle, even when no one looks outside to see the phase. The silent world had become part of human civilization without anyone yet knowing what its surface was made of. That would change when glass lenses were turned toward it, and the smooth celestial lamp of tradition suddenly broke apart into mountains, shadows, valleys, and scars. The telescope did not merely bring the moon closer, it destroyed an ancient idea. For centuries, much of European natural philosophy had treated the heavens as a realm fundamentally different from Earth, perfect, smooth, unchanging, and untouched by the corruption believed to define the world below. The moon, because it visibly changed phase and displayed dark markings, had always been an awkward object within that system. But from the ground, its surface could still be imagined as polished, translucent, or somehow flawless in a way human eyes could not fully understand. Then, in the early 17th century, a small tube of wood and glass turned toward the night sky, and the perfect moon began to fall apart. Galileo Galilei was not the first person to build a telescope, nor was he certainly the first to point one upward. But in 1609, he improved the instrument, observed the moon repeatedly, and understood the implications of what he saw. Near the boundary between lunar daylight and darkness, the terminator, the line was not smooth. Bright points appeared inside the dark side while nearby regions remained unlit, and shadows stretched away from illuminated ridges. To Galileo, this behavior resembled sunrise over terrestrial mountains. Peaks caught the sun before the lower ground around them. Valleys remained dark after surrounding highlands had brightened. By comparing shadow lengths and using geometry, he estimated the heights of lunar mountains, concluding that some were comparable to, or even larger, than mountains on Earth. The measurements were imperfect, but the underlying insight was devastatingly clear. The moon had terrain. It was not a flawless celestial sphere. It had elevation, roughness, cavities, and landscapes shaped by physical processes. In his 1610 publication, Sidereus Nuncius, or The Starry Messenger, Galileo described the lunar surface as uneven and full of hollows and prominences, language that challenged more than a picture of the moon. It challenged the intellectual boundary separating heaven from earth. If mountains existed above, then perhaps celestial bodies were not made from a perfect substance, obeying a completely separate set of rules. The telescope had revealed no monsters, cities, or divine palaces. It had found something more disruptive: a world. The discovery was not accepted without resistance. Some defenders of traditional cosmology argued that the moon might still possess an invisible smooth shell surrounding its visible irregularities, preserving its theoretical perfection. The proposal now sounds like an attempt to protect a conclusion from evidence, but it reveals how difficult it can be to abandon a system that has organized reality for generations. An observation never enters an empty mind. People interpret it through the concepts they already trust, and when new evidence threatens an entire framework, even intelligent observers may first try to absorb the evidence without surrendering the framework. Galileo's images themselves were also not self-explanatory. Early telescopes produced narrow, distorted views with color fringes and limited clarity. A person unfamiliar with telescopic vision could doubt whether the shadows were real features or flaws in the glass. Skilled drawing became part of the scientific argument. Galileo's lunar sketches translated an unstable image into a form readers could examine, but they also introduced artistic judgment. He emphasized light and shadow to communicate depth, and historians continue to discuss exactly how closely some drawings matched specific observations. This does not weaken the discovery. It shows that early telescopic science depended on a chain of trust connecting instrument, eye, hand, geometry, and reader. The moon had become visible in a new way, but learning how to believe that visibility took time. Galileo was also not alone. The English astronomer Thomas Harriot made telescopic drawings of the moon in 1609, possibly before Galileo's famous observations, though he did not publish a sweeping interpretation with the same speed or influence. Other observers soon followed, and each improvement in optics revealed more complexity. What began as a challenge to celestial perfection became a race to map an unfamiliar landscape. Yet mapping the moon presented a peculiar problem. Every observer saw the same hemisphere, but changing sunlight transformed the appearance of its features. A crater visible as a dark hollow near the terminator could nearly vanish under high illumination. A mountain range could appear dramatic at lunar sunrise and flat 2 weeks later. Lunar cartography therefore required repeated observation, careful orientation, and an understanding that shadows were not fixed markings, but temporary clues to shape. The first maps varied widely in accuracy and style. Some looked like geographic charts. Others resembled symbolic diagrams. Names were assigned to features that no human had visited, and naming became a subtle act of possession. In the 1640s, Johannes Hevelius produced an influential lunar atlas based on years of observation from Danzig, now Gdansk. He treated the moon almost as an extension of terrestrial geography, applying names associated with places on Earth. His detailed engravings showed mountains and plains with a richness that made the moon seem less like a light and more like a country. Around the same period, the Jesuit astronomers Francesco Maria Grimaldi and Giovanni Battista Riccioli created another mapping system. Riccioli named many dark regions as seas and oceans: Mare Imbrium, Mare Serenitatis, Oceanus Procellarum, and assigned major craters the names of philosophers, astronomers, and scholars. Ironically, Riccioli himself opposed the heliocentric model, yet the naming system associated with his work became the foundation of modern lunar nomenclature. Scientific history rarely moves in clean ideological camps. A person can resist one transformative idea while contributing permanently to another. The dark plains received emotional names such as the Sea of Tranquility, the Sea of Crises, the Sea of Clouds, and the Ocean of Storms, reflecting a poetic geography imposed on a dry world. Those names preserved the old illusion of water even as telescopes made the surface increasingly physical. The moon became more accurately known while remaining wrapped in metaphor. For a long time, the origin of its circular depressions remained disputed. Many early observers interpreted them as volcanic structures, partly because volcanoes were familiar examples of circular mountains with central openings. The moon appeared covered in ring-shaped formations, some with central peaks, and without a developed science of impact cratering, volcanic explanations seemed reasonable. Others suggested bubbles, collapses, or processes no longer active on Earth. The idea that impacts created most lunar craters gained strength slowly. On Earth, recognized impact structures were rare and often obscured, while active volcanoes were visible and dramatic. Even into the 19th and early 20th centuries, important scientists continued debating whether lunar craters were primarily volcanic or caused by objects striking the surface. The shift toward the impact interpretation required experimental work, comparisons with terrestrial structures, improved knowledge of meteorites, and eventually the recognition that collisions had played a major role throughout solar system history. The argument is a reminder that seeing a shape is not the same as knowing its cause. The telescope revealed circular scars, but their meaning remained hidden for centuries. Another mystery concerned the moon's motion. It seemed to keep one face turned toward Earth, leading to the common misconception that it did not rotate. But if the moon truly moved around Earth without turning, observers would gradually see every side of it. The fact that nearly the same face remains visible means the moon rotates once during each orbit. Its rotation and revolution are synchronized through tidal locking. Even so, the visible hemisphere is not perfectly fixed. Through a subtle apparent rocking called libration, observers on Earth can gradually see about 59% of the lunar surface over time. Part of this effect comes from the moon's elliptical orbit. Its orbital speed changes while its rotation remains more uniform, allowing us to glimpse slightly around its eastern and western edges. Another part results from the tilt of its rotational axis and from viewing geometry across Earth's own diameter. Libration made lunar mapping possible beyond the exact central hemisphere, but it also teased observers with the existence of a region that remained almost entirely concealed. For centuries, the far side was not merely unexplored, it was visually inaccessible from Earth. No improved ground-based telescope could reveal it. The missing hemisphere became a boundary imposed not by distance alone, but by orbital mechanics. Before spacecraft, any map of the complete moon necessarily ended in uncertainty. As telescopes improved through the 18th and 19th centuries, lunar observation became more systematic. Tobias Mayer created detailed maps and precise tables of lunar motion, work linked to one of the era's most urgent practical problems, determining longitude at sea. Latitude could be estimated from the height of celestial objects, but longitude required knowing the difference between local time and the time at a reference location. One proposed solution, the lunar distance method, used the moon's position relative to stars as a kind of celestial clock. Because the moon moves noticeably against the background sky from hour to hour, a navigator could measure its angular distance from a known star, compare the result with published tables, and infer the time at a reference meridian. The method demanded accurate instruments, reliable calculations, and corrections for the observer's location and atmospheric effects. It was difficult, but it connected refined lunar theory directly to survival and commerce on Earth. The moon was no longer only an object of philosophical debate. It became part of a global navigation system. Better predictions required better understanding of gravitational interactions, and irregularities in the moon's orbit tested the work of mathematicians from Newton onward. The moon responds not only to Earth, but also to the sun, and the three-body interaction produces complicated variations that resisted simple calculation. Isaac Newton's law of universal gravitation explained why the moon remains in orbit, but producing highly accurate lunar tables became a demanding mathematical challenge for later astronomers. The moon helped expose the power of gravitational theory while also revealing its computational difficulty. It was close enough to observe precisely and complex enough to punish incomplete models. Photography introduced another revolution. In 1840, John William Draper produced one of the earliest successful photographic images of the moon. Photographs seemed to promise freedom from the subjectivity of drawing, creating a permanent record that could be compared, enlarged, and measured. Yet early lunar photography had its own limitations. Long exposure times, imperfect emulsions, atmospheric turbulence, and loss of fine contrast. Drawings did not disappear immediately because trained observers could sometimes represent fleeting details more clearly than primitive cameras. Over time, however, photographic atlases transformed lunar mapping. Features could be studied by researchers who had not been present at the telescope, and images taken under different lighting conditions could reveal the shape of terrain. By the late 19th century, the moon had become one of the most photographed objects in the sky, its surface divided into named formations and studied as a geological world, even though its geology was still poorly understood. With greater detail came greater temptation. Some observers reported transient lunar phenomena, brief glows, color changes, hazes, or alterations in the appearance of features. A few may have resulted from changing illumination, atmospheric distortion, observational error, or the eye's tendency to find change where none exists. Others were interpreted as possible signs of volcanic activity or escaping gas. The subject remains controversial because most historical reports cannot be independently verified, and modern monitoring has not confirmed dramatic widespread activity. Still, the reports helped keep open the question of whether the moon was entirely dead. Science advanced not by accepting every strange observation, but by asking which ones could be repeated and what physical mechanisms might produce them. Speculation about lunar life also survived long after the telescope revealed a harsh landscape. Some writers imagined inhabitants, vegetation, canals, or artificial structures, often extending terrestrial expectations into a world whose conditions were not yet known. In 1835, the famous Great Moon Hoax, published by the New York Sun, claimed that astronomer John Herschel had discovered fantastic lunar creatures and civilizations through an enormous telescope. The reports were fabricated, but many readers found them believable because telescopes had already revealed wonders that previous generations would have considered impossible. The hoax exploited a moment when scientific authority was growing faster than public ability to verify scientific claims. The moon had become close enough to imagine in detail, but remained distant enough to hold almost anything. Gradually, spectroscopy and physical astronomy stripped away some of those possibilities. The moon showed no substantial atmosphere, no visible oceans, and no obvious signs of vegetation. Measurements of temperature and reflected light suggested an environment far more severe than Earth. Yet the end of one fantasy created a deeper mystery. A dead-looking world covered in craters could preserve history with extraordinary fidelity. Its lack of weather and oceans was not simply an absence, it was a condition that allowed ancient events to remain visible. By the 20th century, astronomers possessed increasingly accurate maps of the near side, photographs of mountains and plains, and mathematical predictions of the moon's motion. But they still did not know the exact age of its surface, the composition of its rocks, the depth of its dust, or the appearance of the hidden hemisphere. Telescopes had shattered the perfect moon, replacing it with a rugged physical world, yet they had reached the limit of what distance could reveal. To answer the remaining questions, observation would have to leave Earth. Machines would have to cross the darkness, circle the moon, photograph the side no human eye had ever seen, and finally descend toward the scarred ground itself. The first machines sent toward the moon were not built only to answer scientific questions. They were launched into a conflict on Earth, where two superpowers had begun treating space as a stage on which engineering skill, political ideology, military power, and national confidence could all be displayed at once. By the late 1950s, the Moon was still physically untouched by humanity, but it had become the most visible prize in the Cold War. Reaching it required solving problems no civilization had faced before: how to accelerate a machine beyond Earth's gravitational hold, guide it across hundreds of thousands of miles, correct its path without a road or atmosphere, communicate through deep space, survive radiation and temperature extremes, and either strike, orbit, land, or return without losing control. Failure was common because almost every component was being tested at the edge of what technology could do. Rockets exploded, signals vanished, guidance systems drifted, and spacecraft missed their target or fell silent before arrival. Yet each failure contained measurements, and each measurement narrowed the distance between imagination and contact. The Soviet Union reached the first major milestones. In 1959, Lunar 2 became the first human-made object to reach the lunar surface, ending its journey not with a controlled landing, but with an intentional impact. It carried no astronauts and returned no rocks. Yet its arrival proved that a spacecraft could cross the space between Earth and Moon. Only weeks later, Lunar 3 flew around the Moon and photographed much of the far side for the first time. The images were blurred and streaked, developed aboard the spacecraft and transmitted through a fragile radio signal. But they revealed a hemisphere fundamentally different from the familiar face seen from Earth. The far side contained fewer of the broad, dark plains that dominate the near side, and far more rugged highland terrain. For the first time in human history, the hidden half of another world had become visible. Not through a stronger telescope, but because a machine had physically traveled beyond the limits of earthbound sight. The photographs did more than complete a map. They demonstrated that the Moon's two hemispheres had experienced different geological histories, opening a puzzle that scientists are still working to fully explain. The next challenge was landing. No one knew with complete confidence what the surface would do beneath a spacecraft. Some researchers worried that the lunar dust might be deep and dangerously loose, allowing a lander to sink. Others expected a firmer surface, but predictions based only on remote observation could not eliminate the uncertainty. In 1966, the Soviet Luna 9 achieved the first successful soft landing and transmitted panoramic images from the ground. Its survival showed that the surface could support a spacecraft. American surveyor missions soon landed as well, sending back thousands of photographs, testing the mechanical properties of the soil and analyzing surface material. These robotic scouts were not glamorous compared with the human missions that followed, but they carried much of the risk first. They examined possible terrain, proved landing techniques, and replaced imagined dangers with measured ones. Before astronauts could walk on the Moon, machines had to teach engineers that the ground would hold them. By then, the competition had accelerated dramatically. In 1961, President John F. Kennedy committed the United States to landing a person on the Moon and returning that person safely to Earth before the decade ended. The goal was scientific in part, but its scale and deadline were political. The Soviet Union had already launched the first artificial satellite and the first human into space, leaving the United States afraid that it was losing not merely a race, but the future itself. A lunar landing offered a clear finish line that the entire world could understand. Yet the United States did not possess the technology required to achieve it when the promise was made. NASA had to develop powerful launch vehicles, navigation computers, spacesuits, life support systems, tracking networks, docking procedures, lunar landing engines, heat shields, and thousands of smaller systems whose failure could end a mission. Project Mercury tested whether humans could survive and function in space. Gemini developed longer flights, spacewalks, rendezvous, and docking, the quiet techniques without which Apollo could not work. Apollo then attempted to combine them into one of the most complicated journeys ever designed. The program's progress was not smooth. In January 1967, astronauts Virgil Gus Grissom, Edward White, and Roger Chaffee died when a fire broke out inside the Apollo 1 command module during a ground test. The accident exposed serious problems in design, materials, procedures, and communication. NASA halted crewed Apollo flights while the spacecraft was extensively redesigned. The tragedy did not make success inevitable or noble by itself. It showed how dangerous institutional urgency could become when confidence moved faster than caution. The later achievements of Apollo were built partly on the painful recognition that engineering discipline had to be stronger than pressure to meet a schedule. In December 1968, Apollo 8 carried Frank Borman, Jim Lovell, and William Anders around the Moon. They did not land. They entered lunar orbit, passed behind the far side beyond direct radio contact, and became the first humans to see Earth as a complete world rising above another world's horizon. Anders's photograph, later known as Earthrise, compressed the meaning of the mission into a single image, a small blue and white sphere suspended above a gray, lifeless foreground. The photograph did not reveal a new scientific fact in the strict sense. People already knew Earth was a planet, but it changed the emotional geometry of human existence. The Moon, once the object being sought, became the distant shore from which Earth could finally be seen as one fragile place. 7 months later, Apollo 11 descended toward the Sea of Tranquility. Neil Armstrong and Buzz Aldrin rode inside the lunar module Eagle, while Michael Collins remained in orbit aboard Columbia. The final descent was far from automatic or calm. Computer alarms sounded as the guidance system became overloaded, and Armstrong saw that the planned landing area was covered with rocks. He took partial manual control, guiding the spacecraft forward while fuel reserves narrowed. On July 20, 1969, the lunar module landed safely. When Armstrong stepped onto the surface, the moment became one of the most watched events in history. But the science began almost immediately. Armstrong and Aldrin photographed the terrain, collected soil and rocks, placed instruments, and deployed a laser reflector. They spent only a little more than 2 hours outside, yet the material they returned began overturning older ideas about the Moon. The dark ground of Mare Tranquillitatis was not dried mud, ocean sediment, or recent volcanic ash. It consisted largely of ancient basalt produced by lava flows more than 3 billion years earlier. The samples showed that the lunar maria were the solidified remains of a volcanic past, confirming geological interpretations that remote observation alone could not securely date. They also contained impact-produced glass, fragments welded together by collisions, and grains altered by long exposure to the solar wind. The Moon rocks were almost entirely free of the effects that constantly rewrite rocks on Earth. They had not been softened by rain, buried beneath oceans, folded by plate tectonics, invaded by roots, or repeatedly recycled through a living planet. They carried records from an age Earth had largely erased. Apollo 11 was only the beginning of the scientific campaign. Apollo 12 made a precision landing near Surveyor 3, allowing astronauts to visit a robotic spacecraft that had been sitting on the Moon for more than 2 years and return some of its components for study. The rendezvous demonstrated that astronauts could land close to a chosen target, an ability essential for reaching geologically valuable locations rather than merely safe open plains. Apollo 14 explored the Fra Mauro Formation, a region covered by material thrown outward during the enormous Imbrium impact. Apollo 15 marked a major shift toward exploration, driven more explicitly by geology. The mission carried the first lunar roving vehicle, allowing astronauts David Scott and James Irwin to travel farther from their lander and examine a wider range of terrain. Near Hadley Rill, they collected a pale anorthosite, later nicknamed the Genesis Rock. It was not literally the first rock on the Moon, but it represented part of the ancient crust formed when light minerals floated upward through the early magma ocean. Holding it was like holding a surviving fragment of the Moon's first solid exterior. Apollo 16 then landed in the Descartes Highlands, where scientists had expected terrain that might have been formed by volcanism. The returned samples told a different story. Much of the region consisted of impact breccias, rocks made from fragments crushed, mixed, heated, and welded together by collisions. The result forced researchers to revise maps and abandon interpretations that had seemed convincing from orbit. That was one of Apollo's most important scientific achievements. The rocks did not merely confirm existing theories, they proved some of them wrong. Apollo 17, launched in December 1972, became the final crewed lunar landing of the 20th century and the most scientifically ambitious of the Apollo surface missions. Its crew included Harrison Schmitt, the first professional geologist to walk on the Moon. With Commander Eugene Cernan, Schmitt explored the Taurus-Littrow Valley, a site chosen to provide access to both ancient highland material and signs of comparatively younger volcanic activity. They discovered orange soil composed largely of tiny volcanic glass beads, evidence of explosive eruptions driven by gases released from deep lunar magma. The color seemed almost impossible against the gray landscape, a sudden stain of ancient fire preserved in a world long assumed to be uniformly dead. Schmidt's training mattered because geology depends not only on collecting objects, but on reading relationships, layers, contacts, fragments, slopes, and the position of a rock within a larger landscape. A sample removed without context can answer chemical questions. A sample understood in place can help reconstruct an event. By the time Cernan and Schmitt departed, 6 Apollo missions had successfully landed astronauts on the Moon. 12 people had walked there, and the crews had returned approximately 842 pounds, or 382 kilograms, of rocks, dust, pebbles, core samples, and broken material. The Soviet Union also achieved robotic sample returns through the Lunar program, proving that lunar soil could be collected and brought to Earth without a human crew. These Soviet samples were much smaller in quantity, but they came from different locations and added valuable evidence beyond the Apollo landing zones. Together, the returned materials transformed the Moon from a distant astronomical body into a world that could be examined in laboratories grain by grain. Their chemistry revealed a deep relationship between Earth and Moon. Lunar and terrestrial rocks showed striking similarities in several isotopic signatures, strengthening the idea that the Moon formed from material closely connected to the early Earth, though the exact mechanism remained debated. The samples were extremely depleted in many volatile substances compared with typical Earth rocks, suggesting a history involving intense heating, loss, or redistribution of easily vaporized materials. At the same time, later studies found traces of water and other volatiles inside volcanic glass and minerals, correcting the earliest picture of a Moon that had always been completely dry. The conclusion became more complex. The Moon had lost much of its volatile inventory, but not necessarily all of it. The rocks also revealed that the bright highlands were older than the dark Maria, supporting the model of an early molten moon that formed a light anorthositic crust before later basaltic eruptions filled great basins. Radiometric dating provided ages for specific samples, giving scientists fixed points with which to calibrate the crater counting method used across the solar system. Because of Apollo, a cratered plain on Mars, Mercury, or an asteroid could be assigned a better estimated age. The stones changed not only lunar history, but the chronology of planetary science itself. Instruments left on the surface extended the discovery beyond the samples. Seismometers detected moonquakes, meteorite strikes, and vibrations that revealed clues about the moon's interior. Heat flow experiments measured energy escaping from below, though the Apollo landing sites represented only a small portion of the near side. Solar wind collectors trapped particles arriving from the sun. Laser reflectors made it possible to measure the Earth-Moon distance with extraordinary precision for decades afterward. The missions were brief, but some of their experiments continued speaking long after the astronauts left. Perhaps the most scientifically far-sighted decision was not to analyze every sample immediately. NASA preserved substantial portions under controlled conditions, recognizing that future instruments would be more sensitive than anything available in the 1960s and 1970s. That decision turned the Apollo collection into a scientific inheritance. Decades later, researchers have opened specially stored cores and used techniques their original collectors could not have imagined, studying tiny chemical signatures, trapped gases, ancient magnetic fields, volcanic water, impact histories, and the timing of the moon's earliest transformations. The rocks have not finished changing science because scientific questions and instruments continue to change around them. This is also why claims that the moon landings produced nothing beyond political theater misunderstand what returned to Earth. The flags, speeches, and footprints carried enormous symbolic power, but symbolism was not the program's only legacy. A political race delivered a geological archive. Competition designed to demonstrate national superiority ended by revealing that Earth and Moon shared a violent beginning, that planetary surfaces could preserve billions of years of history, and that the early solar system had been far more dynamic than the calm arrangement seen today. Yet Apollo also left a strange silence. After Cernan climbed back into the lunar module in December 1972, no human followed. The machinery was dismantled, priorities changed, budgets moved elsewhere, and the most distant place humanity had reached became a place known mainly through old recordings, preserved footprints, orbiting spacecraft, and sealed stones in laboratory vaults. The moon had been conquered only in the language of headlines. Scientifically, 6 landing regions were not an entire world. Nearly all the human sites lay on the near side and close to the equator. The far side remained unvisited by people. The poles were still poorly understood, and vast regions capable of answering fundamental questions had never been sampled. Apollo proved that humans could reach the moon, and that its rocks could rewrite planetary history. It did not complete that history. It revealed how much remained hidden, and how valuable the next handful of lunar soil might become. Thank you for spending this quiet journey with sleepy cosmic lore. If you enjoyed exploring the universe together tonight, please like this video and subscribe to support the channel. Your support, no matter how small, truly means a lot.